Hey guys, this is Mrs. B going on round 2 of recording the accumulation function after losing my last recording. So we are on lesson 29, and we're going to go ahead and continue on with our understanding of the concept of a definite integral. So we basically have come to terms with the fact that the definite integral is nothing more than area. So we are going to consider a very special type of problem. Let's go ahead and take a look at the function f of x equals 2. And we know that that is a horizontal line as shown in the figure over here. And realize that the equation of the graph f of x is equal to 2 is the same as if we said f of t equal to 2 or if we said f of k equal to 2. It doesn't matter what we use, x, t, or k, the graph is still going to be a horizontal line. So we are going to go ahead and graph it using, I guess, x if you need to see it that way. But we're occasionally going to be calling it another variable. And in this particular case, they called it f of t equals 2, all right, where t is your x value, f of t, or y, is your y value. Now, the expression, the integral from 0 to x of f of t dt, now that is a function of x. And the reason why it's a function of x is because it represents the area under this f of t curve, starting at time equals 0 and ending at time equals x. What that means that is a function of x is that means if I say evaluate this at, let's say, x equals 5, you're going to plug a 5 in for x. That's what it means when you say something is a function of x. It means that you're going to plug in x values to evaluate it, to do something with it. So that's why we needed f of t dt, because t is the horizontal axis and x is our input, and our input becomes the endpoint. It's where we're stopping on the t line to, in your case, to draw the box and decide, okay, what's the area under the curve, length times width, and calculate that area. So I hope that kind of made sense. So let's say we want to actually do a chart, okay? We want to do a chart, and we want to find the different values for x. So when we say at x equals 0, we are plugging in 0 into x and taking the integral from 0 to 0 of f of t dt, and this is f of t right here. And the integral from 0 to 0 is simply 0. Then we're going to go ahead and plug in at x equals 1. So the integral from 0 to 1 of f of t dt, 0 to 1 is this rectangle right here, which has an area of 2. And you do the same thing over and over again. We do from 0 to 2 of f of t dt. So now we're taking that rectangle, and that rectangle, pardon my drawing there, that rectangle has an area of 4. And continue on in that direction until you get to 5, from 0 to 5, and that rectangle has an area of 5 times 2, which is 10. So it should be clear that as x gets larger, in this case the integral from 0 to x of f of t dt is increasing as well. So what we're doing is we are accumulating area. If you notice, we started with no area from 0 to 0. Then we went from 0 to 1 and we had an area of 2. Then we have from 0 to 2, and we had an area of 2 and 2, which made 4. And so on, 2 and 4, that made 6. And so on and so forth. To accumulate, or 4 and 2, actually, to make 6. To accumulate that area up until from 0 to 5, we've accumulated to 10. And this is called the accumulation function. The integral from 0 to x of f of t dt. And I just explained to you why we used f of t instead of f of x, because when we're plugging in at x equals 5, where would we be putting that 5? Would we be putting it here or here? Well, we want to put it up here, and this is going to be f of t dt, which is our function. So let's go ahead and take a look at the function f of x equals 2 of x. Let's calculate the value of the accumulation function from x equals 0 to 4. So we have the integral from 0 to x of f of t dt. We're going to, as our quote-unquote y values, we're going to calculate them at the following x values. f of t is going to be 2x, which we've graphed over here on the side. Ignore this dotted line graph for a second. We've graphed f of t equals 2x right here. It is a line with a y-intercept of 0, slope of 2. So if we go ahead and plug 0 into the accumulation function, we're doing the integral from 0 to 0 of f of t dt, which is 0. If we plug 1, we're doing the integral from 0 to 1, so from 0 to 1, which gives us this triangle right here that has an area of 1. From 0 to 2 gives us this triangle, accumulating those areas to get an area of 4. 0 to 3, keep going, gives us an area of 9. 0 to 4, draw that last big triangle here, accumulating all of those, gives us an area of 16. So if we plot those values on the same graph, which is what was there that you can't see, plotting those values on the same graph, let me go ahead and show you. If we have x equals 0 and y equals 0, x equals 1, y equals 1, and so on and so forth. Oh, that's not my pen. Okay, 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. And plot that right there. You should recognize that curve. You should also recognize that curve. Look at these values. What do you notice? They are squares. So the curve is a y equals x squared. Take a look at that. Y equals x squared, and where it came from, y equals 2x. So if we take the derivative of this, we end up with y equals 2x. Come on, move, move, move. There we go. We end up with y equals 2x. So we started with y equals 2x. We integrated it, we accumulated it from 0 to 0, from 0 to 1, from 0 to 2, from 0 to 3, 0 to 4, boom, 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 boom. Plotted those, came up with y equals x squared. So the derivative of that y equals x squared, or the derivative of that accumulation function, leads us back to the function itself. That is important. The derivative of the accumulation function is the function itself. So what we're saying is the slope of the tangent line, the derivative, the slope of the tangent line of the accumulation function is the function itself. Like I said, if we start with a function, we accumulate it, then we take its derivative, we end up back with the function. So that should start your wheels spinning that the accumulation function and the derivative have some form of inverse relationship. And they do. So that's going to get us thinking towards what's coming up, which is the fundamental theorem of calculus. So just, if you need to rewind that and hear it again, that's really important. So what we're going to do now is actually put some of these concepts into practice.